Now we come to lecture 12 and the second part of the unit 2 is engine parameters and knocking. We will first study that for spark ignition engines, and in the next lecture we will study engine parameters and knocking in compression ignition engines, that is the diesel engines. First let us come to the petrol engines, the combustion stages in spark ignition engines. We are talking about ignition now. We know that the ignition takes place at the end of the compression stroke, just before the piston reaches the TDC. Fine? So let's read this and understand. There is a certain interval of time between the instant spark is given, that is at the end of the compression stroke, and when there is a noticeable rise in the cylinder pressure due to combustion. Spark is given, combustion starts, and when there is a noticeable rise, there is a lag. Pressure rise doesn't take place immediately. It takes place after a small bit of time, which is called ignition lag. This time interval during which the mixture near the spark plug gets heated up to its self-ignition temperature, SIT. Self-ignition temperature means it ignites on its own at a certain pressure and temperature, gets ignited and gives rise to a self-propagating nucleus of flame is called ignition lag. What I'm trying to say is there is a ignition lag. The instant the spark is given, there is a pressure rise, does not take place instantly. It takes place after a certain time period, which is called the ignition lag. See in the diagram, this is cylinder pressure, this is the crank degrees, this is 0, means top dead center. This is when the spark is given just before the TDC. Minus 100 degrees and 100 degrees, this part only has been taken. This is the crank degree, this is the cylinder pressure. So A to B is the ignition lag. Once the combustion increases, pressure rise, then it increases from, the cylinder pressure will increase immediately from B to C. Let us read it. After the ignition lag period, that is after B, the flame spreads throughout the mixture. The flame spreads throughout the mixture is of air and fuel, causing a rapid rise in cylinder pressure, and temperature. Thus, the complete combustion takes place in two stages, that is A to B, which is ignition lag, which is the first stage, which is called the ignition lag. The second stage, BC, corresponds to the propagation of flame in the combustion chamber. Once the fuel-air mixture catches fire, a flame is produced on the complete length of it, like a tsunami, you could say. And then the flame moves together as a front. Like the waves in the ocean, you see, they move as one. Similarly, this flame moves like that. Can we see? The second stage starts when the first measurable rise of cylinder pressure can be seen on the indicator diagram. We have studied the indicator diagram earlier. And ends when the peak pressure is attained. The C is the peak pressure. However, note that these two stages are not entirely distinct because there is no clear dividing time between them. Meaning that this point A to B, B to C, there will be a slight overlap. There is no clear it may, nobody has been able to find out where exactly there may be a little overlap what that means to say. It's not necessary then. Moreover, again, this is one point. Again, moreover, the combustion is not necessarily complete. Is not necessarily complete at the end of the second stage. Combustion is not. There may be some fuel-air mixture left. Some fuel may burn after point C. Some fuel may burn after point C. We will see this, the end gas that will come subsequently after point C. At the end, after point C, during the expansion stroke. After the compression stroke, we know comes the expansion stroke, and some of that air fuel mixture may burn during the expansion stroke. This burning of fuel after the point of maximum cylinder pressure C is generally called afterburning. Means any burning after the peak pressure attained is given the term afterburning. You must be conversant with these terms. And incidentally, this is a very interesting topic. A lot of knowledge you get as mechanical students. What happens inside the IC engine for a petrol and a diesel engine. These terms must be remembered. Now we come to pre-ignition and detonation in spark ignition system engines. Pre-ignition. We will study pre-ignition and auto-ignition. There is a difference between the two. Once you read it, you will come to know. Pre-ignition. The speed of the flame propagation after igniting the mixture mainly depends on the amount of turbulence and also on temperature and pressure before ignition. As I said, once the mixture catches fire, a flame front is produced, and the speed, of course, this flame has to spread all around the cylinder to get the maximum power output. The whole mixture must burn, and that will depend on the turbulence. And let me tell you, when we study ahead, turbulence is deliberately created. One of the ways is the piston head is modified in such a sense that it causes turbulence. There are other ways also to cause turbulence by the intake of the air. Various means are there which we will study later, and also on the temperature and pressure before ignition. So these three factors will decide the pre-ignition. Now how does it occur? Let us see. What happens when pre-ignition takes place? Ignition should not start before the spark has passed. We know that. The spark plug has been kept on top of the cylinder to give that ignition. That ignition spark is provided by the spark plug. So if something happens before, if the ignition takes place before the spark plug fires, something's wrong. So let us see what. Should not start. But this may sometimes occur. It does occur sometimes due to certain hot spots of carbon in the combustion chamber. Hot spots in the cylinder lining or also on the spark plug itself, or due to overheating of the spark plug points. Overheating, then it becomes red hot, it's overheated, and pre-ignition takes place. This is called pre-ignition. This is what is meant by pre-ignition. That is, before the spark is passed, the ignition of the combustible mixture takes place. Now, what is the effect? When pre-ignition occurs, its effect is the same as that of a very advanced ignition timing. And it is before the spark plug is fired, it has ignited. That means it's equivalent to something like advanced ignition timing, and we know the effects of advanced ignition timing are not so good. What it causes is a serious loss of engine efficiency and output. Why loss? Because the desired way in which the charge must burn is not happening. It's burning before the piston reaches the TDC, or just after the TDC. It's all planned, but it's not going as per the design of the engine. So there is a loss of engine efficiency and the output, because the charge is not burning uniformly and not completely also. When pre-ignition may be detected. How do we find out whether it's pre-ignition? As a layman, by shutting off the engine. Shut off your scooter engine, and if the engine still keeps firing, that means pre-ignition is taking place. There are hot spots inside the cylinder, or the spark plug is overheated, whatever it is, and engine continues firing. Another indication is the sudden loss of power without any engine mechanical malfunction. There is no malfunction, but still you suddenly find that there is a loss of power. You're trying the accelerator on your motorcycle, scooter, it's not accelerating, it's not moving the way it should. That was pre-ignition. Pre-ignition is due to certain hot spots. It could be on the spark plug, red hot spark plug, or hot spots due to carbon deposits. Hot spots due to carbon deposits. Now that was pre-ignition. What is auto-ignition? Auto-ignition is automatically, it ignites on its own the air-fuel mixture. Let us read it. If fuel-air mixture is rapidly compressed so that its temperature exceeds the self-ignition temperature of the mixture, it may undergo auto-ignition or self-ignition. Means if it is compressed too early and it attains its self-ignition temperature, you know every combustible material has a self-ignition temperature. You reach that temperature and it will ignite on its own, so that its temperature exceeds temperature, it may undergo auto self-ignition, even though no spark plug is present. No spark is present. That is, spark plug is yet to fire, but due to the fuel-air mixture being compressed and the self-ignition temperature of that mixture, of that fuel, especially air is common, is reached and it auto-ignites. Self-ignition temperature is the characteristic of a fuel-air mix and varies from fuel to fuel. Self-ignition temperature of diesel will be different, of petrol will be different, of gas it will be different. There are various fuels these days, all have a separate, different self-ignition temperature. Experimentally seen that auto-ignition of mixture does not, now this is the research into it, does not occur instantaneously as soon as the self-ignition temperature is reached. This is temperature, this is time. This is the self-ignition temperature. This temperature, self-ignition temperature. So naturally below the self-ignition there will be no explosion. It is yet to reach. When it only reaches the SIT, then only the mixture will catch fire and burn. But once, so there is no explosion. This is no explosion. Once it crosses the SIT and this is an increase of temperature, we will find that this is the delay period will increase. But with the increase of temperature, this delay period will reduce. So even with pressure, temperature and pressure, as you increase it, there is a certain delay. That delay period will reduce before this. So we desire a low delay period. This is what we desire. experimentally seen that auto-ignition of mixture does not occur instantly as shown in SIT is reached, occurs when the mixture stays at a temperature equal or higher than the self-ignition temperature. Equal to or higher than the self-ignition temperature for a finite period of time called the delay period. That means for a certain period, it does not immediately auto-ignite, it auto-ignites after a small delay period, which is after a period called the delay period. This depends on the nature of the fuel and also on the pressure and temperature of the mixture. Higher the temperature above the SIT, smaller the delay period. Higher the as you go up, this delay period will gonna go up. Now it's reduced. This is the delay period. At this temperature, this is the delay period at this temperature. Higher the pressure, similarly, higher the pressure, smaller the delay period. Auto ignition of mixture is caused by chemical reactions between the fuel and air during the delay period. During this delay period, there are chemical reactions between the air and the fuel. Fuel is nothing but carbon-based fuel, and the chemical reactions between them causes the delay. That's why the preparation of petrol and diesel is not an easy process. We must have read in physics also, or in the first semester, that extraction of fuel, how fuel is made, how diesel, various parts of that chart. Detonation or knock in SI engine. Now we study what is detonation, or it's also called knock, or even blinking in SI engine. So the spark flame, we know when spark has caused ignition of the combustible material and the flame front is made. The flame front travels across the combustion chamber in an orderly manner. Fine, initially it travels in an orderly manner. Pressure continues rising uniformly in the combustion chamber. So let us focus attention on the last part of the unburned charge which we had seen, called the end gas. That is after that point B. Unburned gas we had studied after the last point rule, the highest pressure. There is a point B, point C. A to B was the ignition lag, B to C. After point C, what's called the certain unburnt charge was there, which we had seen on this back of this. That is called the end gas. The end gas has experienced, the one after point C, rapid compression during the compression stroke. The purpose of compression when piston moves from BDC to TDC, and later by the advancing flame front. So the flame front has also started moving after the spark plug is fired. The pressure of the end gas and also its temperature, when the flame front is about to reach it, will be almost equal to the peak pressure of the cycle. Almost equal to the peak pressure at C, as most of the charge has burnt by this time. Just end charge is only a few small percentage of the complete charge. This temperature of end gas may exceed the self-ignition temperature of fuel-air mixture, and it may be in the process of the delay period. It may be in the delay period. This end gas may be in the delay period, and the SIT we studied here. The SIT, as its pressure increases, the delay period reduces, and SIT, self-ignition, once it crosses the SIT. So this end gas may burn now in two ways. So up to here we've seen that the flame front is also moving, and also the peak pressure is also attained, point C. This end gas may burn in two ways. The flame front is approaching the end gas. Now let us see. And there is also the delay period factor. Both these factors will come into play in the study of these two ways. This end gas will burn in two ways. If the delay period of the end gas is sufficiently long delay period, the flame front will reach it. If the delay period is long, by that time the flame front will reach it and it will burn out. Will reach it before end of delay period, and the charge will burn in a normal manner. So if there is a longer delay period which is desired, then the end gas, as far as the end gas is concerned, it will burn normally. But if the delay period is short, and it comes to an end before the delay period is short, before the flame reaches the end gas, that is, it's short delay period, and the flame has yet to reach the end gas, and it comes to the end before the flame front reaches the end gas, it may undergo auto ignition. Because the self-ignition temperature has been crossed, although it has not reached the end gas, but it may auto-ignite because the self-ignition temperature has been crossed. Since the conditions throughout the end gas, even the conditions of the end gas are almost similar to the flame front which is moving towards it. The conditions are the same. It will auto-ignite all at once and burn in zero time. So, when the delay period is short, what will happen is that this end gas will auto-ignite. The end gas will, after point C, will auto-ignite all at once and burn in zero time. You must go through this again. That's why I made these notes. Read it again. Second time, third time, you will understand fully. First time, you may be having some problem in understanding. Because of these high pressure waves are traveling with the flame front, this high pressure wave, at a very fast speed through the combustion chamber. The high pressure wave is traveling because of what has happened here. The end gas has burnt instantaneously immediately, because the conditions are above the SIT, high pressure, high temperature. Because these high pressure waves traveling at a very fast speed, a severe blow is delivered against the cylinder walls, producing knocking or pinking. So, knocking or pinking, knocking as we call it, occurs due to the instantaneous burning of the end gas because the delay period was short and the flame front has not yet reached it. Try to understand. This is the crux of this whole thing. This abnormal blow forces the engine structure and its various parts to vibrate, and detonation is said to occur. Tremendous blow, and which will cause the huge explosion, vibrations, which will cause the various parts to vibrate, and detonation is said to occur. Now, having read that, let's see, since this labels detonation and knocking is there, let us see the effects of detonation in spark ignition system engines. We've mostly covered it. This is sort of a revision and some added points. Combustion with detonation. We've seen how detonation occurs due to the immediate burning of the end gas before the flame front has reached it. This was detonation. Let us see the effect. High rate of pressure rise. This we've just covered, caused by simultaneously burning of the end gas, resulting in high stresses in engine parts and mechanical damage. Fine, this we've just covered. Local melting of piston and rings. In fact, this pressure may be 3 to 4 times more than the normal pressure which is supposed to be there. 3 to 4 times is a huge amount. Local melting of piston and rings. This is caused, that means the piston and rings may melt. Serious, stall the engine. Caused by rapid heat transfer from high temperature and pressure gases which force their way past the piston rings. This end gas burning causes even local melting because the temperature rises and pressure rises very high, it burns instantly, delivering a hefty blow all around in the cylinder and the various parts. And the pressure gas which force their way past the piston rings. Otherwise, we know what is blow-by. Even in normal engines when it is running, blow-by is nothing but the combustible mixture or burnt gas seeing their way past the piston rings and falling into the sun. That's why the engine oil has to be changed more often, which I had mentioned earlier. Overheating of the spark plug, another effect of detonation. Owing to violent gas vibrations, hot gases flow repeatedly in and out of the spark plug cavity. We've all seen a spark plug cavity. There's a cavity. We had studied spark plug, in fact, in the previous lecture, if I'm not mistaken. And we had seen the construction. There's a cavity where the two electrodes, there's a gap between the two electrodes which causes a spark. That cavity is there, thus increasing the temperature. Results in a change of increasing its temperature of the spark plug. This results in change of electrical characteristics of the spark plug, rendering it unserviceable. The electrical characteristics, what it's supposed to do, are not performing up to the mark because of this high temperature, and it renders it useless or unserviceable. Pre-ignition, we have studied pre-ignition. Pre-ignition was due to the hot spots or hot spark plug. Pre-ignition, auto-ignition. Pre-ignition is spark plug. If the spark plug picks up too much heat from high temperature gases, it becomes red hot and acts as an ignition source. We have studied this in the previous chart. To ignite fuel air mixture adjacent to it, causing pre-ignition. These hot spots, the mixture which is close to it, usko ignite kar deta hai, and pre-ignition takes place before the spark plug has fired. Thus, detonation can lead to, so this is the effect of detonation will lead to pre-ignition, which in turn would lead to more severe detonation. It's cascading effect. Detonation leads to pre-ignition, pre-ignition leads to further detonation. And this will deliver a massive blow inside the engine to its parts. Would lead to more severe detonation will damage the engine. Fine. Now I am mentioning here dopes. We don't like this knocking and detonation is undesirable property in an engine, and we have to avoid it at any cost. How do we do it? By adding additives. These additives are called dopes, and what is the function? The function is to reduce the anti-knock or detonation properties of the fuel. Certain substances, when added to fuels, even in a small proportion, have pronounced anti-knock effect. We want an anti-knock fuel desirable. the ones we get on the curbside, on the pumps, it's already mixed with it. These additives are called dopes. Indian Oil, Bharat Petroleum, Bharat Gas, they सब पहले ही at the factory stage itself is all mixed in it. Tel is the most common one which is there. It is called tetraethyl lead. Its chemical formula is Pb bracket C2H54 mixed with ethylene dibromide C2H4Br2. This is commercial name is ethylene fluid. It's called ethylene fluid. This is mixed with the petrol. We're talking about petrol. Next lecture will be diesel. So what happens in this case? The addition of ethylene dibromide prevents the deposit of lead inside the cylinder after decomposition of this tel. The tel decomposes and deposits lead. So this ethylene dibromide prevents deposit of lead. And decomposition of TEL takes place at a temperature higher than 210 degrees centigrade. What happens is the lead and bromine combine to form a lead. They form lead bromide, which goes away with exhaust gases. Which goes away with lead bromide is formed, and this goes and the exhaust goes away. The point is that dopes are added because anti-knock is most undesirable, especially detonation is even more dangerous because it has a cascading effect. It keeps on increasing and it may damage the engine very badly. So all this is done at the factory stage itself, but you must be aware of this is also what is the composition of a fuel and why this is added. So we've covered, I think, lecture 11, 12, and the next lecture, or 12, next lecture we will see the engine parameters and docking in the combustion ignition engines, that is the diesel engines. Okay, thank you.